Hello, this presentation introduces prototype surveillance unit for efficient and effective partially relevant video retrieval. Partially relevant video retrieval is a task to retrieve a video that is most relevant to the text query. We say that it is challenging because videos are untrimmed so that only partial moments are relevant to the text query. In PRVR, while the retrieval performance is an important factor, the latency is also another important metric since it directly impacts the user experience on video search platforms. To address PRVR, MSSL introduced exhaustive clip modeling strategy to prepare for all length of clips. For example, given that the video is composed of 3 frames, they encoded clips consisting of single frame to 3 frames. Then, since the exhaustive clip modeling strategy sacrifices efficiency by encoding a lot of clips, GMM introduced local attention clip modeling. To be specific, they modified the attention weight within self-attention to constrain the attention to a local frame with predefined Gaussians. Likewise, GMM achieved efficiency since only the frame number of features are utilized for retrieval. However, we found that they struggle to handle long and complex queries since they mainly focus on local context. Next is the motivation for our work. Although inefficient, we find that exhaustive clip modeling strategy is beneficial since the text query may correspond to long and short clips. So to leverage this benefit and improve the efficiency, we propose prototypical network to aggregate the multi-scale features into a smaller footprint. This is the overview for our prototypical framework. For the video branch, we first encode frame features and construct clip representations. Then, prototype generator aggregates the clip representations into the visual prototypes. For the text branch, after encoding text features, we use attention pooling to make a single query representation. Then, the similarity between the visual prototypes and text token is computed for retrieval. On the right side, we use reconstruction task only for the training. To be more specific with prototype generator, our prototype generator only consists of cross-attention layers. The reason for using only the cross-attention is because independent prototypes are more effective for retrieval as they tend to capture specific events more precisely. On the right side, we illustrate the retrieval training process. So, assuming that there are visual prototypes from 4 videos and the text representation for a text query, we first compute similarity between the text token and all visual prototypes. Then we select only the visual prototype with the highest similarity for each video. Finally, the contrastive learning is performed between these prototypes and the text query. The reason for using only one prototype for each video for matching with text query is because only the partial moment within video may be relevant to the text query. Then, to improve the prototypical learning, we introduced reconstruction tasks. In particular, cross-model mask reconstruction ensures that the retrieved visual prototype fully understands the text query. Therefore, we use the retrieved prototype to reconstruct the text tokens. And the reason for using mask reconstruction is because the same semantics can be expressed through diverse expressions. For example, man and woman are walking can also be expressed as people are walking. So, to minimize the reconstruction errors caused by these expression variations, we used mask reconstruction task, which we can use unmasked text tokens as a reference for how to express the semantics. On the other hand, Unimodal reconstruction is for preventing information loss during prototype aggregation. Specifically, visual prototypes are decoded through MLP decoder to reconstruct video features. Then, we provide weak guidance for the prototypes regarding where to attend, since dense annotations for exact moments are missing. So, we instead first concatenate two different videos, and then construct prototypes for the concatenated videos. And by ensuring that the retrieved prototype for the text query attends to the frames within the paired video, we encourage the prototype's discriminability between different videos. And lastly, although we have improved the prototypical framework in various aspects, we indicate that the capability to generalize across diverse text queries may be limited if semantic overlap exists between prototypes within the same video. To address this, we incorporate an orthogonal objective into prototypical learning to promote prototype diversification. So, to sum up, we propose the prototypical framework that enables the compact encoding of long and complex videos. However, since it does not guarantee the text associativity, preservation of visual information, and diversity between prototypes, we proposed multiple components to enhance the effectiveness. Next is experiment. To evaluate the PRBR performance, we use the recall at K for the metric, and SUMAR indicates the sum of all recall at different Ks. Across 3 PRVR dataset, our method achieves state-of-the-art result and achieves the second best latency. And to examine the prototypes, first, on the left side, we show that the retrieval score is highly correlated with the degree of attendance on frames within the ground truth moment. Specifically, for each query, we sort the prototypes by their retrieval score and average the prototype's attention rate within GT moment. The descending curve validates the high correlation between the retrieval score and prototype semantics. On the right side, we examine the matching frequency of each prototype, showing that all prototypes are actively utilized. In the below tables, we show how performance varies according to the number of prototypes and also compare different designs of prototype generator. Last slide shows the qualitative results. First, at the top, we illustrate that our baseline GMM format struggles with complex queries depicting over long sequences, retrieving a video that contains partial information within the text query. On the other hand, our model retrieves the correct video, identifying 3 sequential contexts within the video. Moreover, the example below show that all top 3 retrieved videos from our model are relevant to the given text query. And this is the end of our presentation. Thank you for listening.